Welcome back to today's Explainer. Today, we're going to demystify how your very own human biology intercepts with the massive, abstract physics of light. The human eye is arguably our most significant sense organ, letting us take in this beautiful, colorful universe. But how exactly does it work in tandem with the light bouncing all around us? Let's find out.
Here's our roadmap for today. 1. The human camera. 2. Fixing vision defects. 3. Prisms and dispersion. 4. Atmospheric refraction illusions. And finally, 5. The colorful sky.
Section 1. The human camera. All right, let's dive right in by looking at this brilliant cross-section of the eye. The eyeball is roughly spherical with a diameter of about 2.3 centimeters. It really is just a beautifully engineered biological device.
Actually, it's incredibly helpful to think of the eye exactly like a camera. First up, you have the cornea. That's the thin outer membrane where light first enters, and it's where most of the initial bending or refraction happens. Just behind that is the iris, which is a dark muscular diaphragm acting just like a camera's aperture. It dictates the size of the pupil, basically regulating the exact amount of light that's allowed to get in. And at the very back, that's your retina. Think of it as your biological film. The lens forms an inverted, real image right on this delicate, light-sensitive screen, which then generates electrical signals that shoot straight through your optic nerve to your brain.
Now, here's where it gets really cool. Your ciliary muscles act as a built-in biological autofocus. Your eye lens is made of this flexible jelly-like material, right? When you're staring at something far away, those ciliary muscles relax, making the lens thinner and increasing its focal length. But when you pull something close to your face, they contract. This makes the lens thicker, curving it to decrease the focal length. We actually call this dynamic autofocus the power of accommodation. But, this biological autofocus definitely has a strict mechanical limit, 25 centimeters. That is the near point for normal vision in a young adult. If you try to read a printed page closer than 25 centimeters, the words are going to blur and you'll start feeling some serious eye strain. Why? Because your ciliary muscles just literally cannot contract to thicken the lens any further than that.
Section 2. Fixing vision defects.
Okay, listen up closely because this next part, it is an absolutely guaranteed board exam question. We really need to understand what goes wrong when the eyeball shape or lens curvature gets a bit messed up. First is myopia, or nearsightedness. If you're myopic, you can see nearby objects perfectly fine, but distant stuff is super blurry. This happens because the lens converges light too strongly and the image actually forms in front of the retina. On the flip side, there's hypermetropia, or farsightedness. Here, distant objects are crisp, but close-up things are blurry. The light just isn't converged enough, so the image ends up forming behind the retina. I highly recommend grabbing a quick screenshot of this summary table. It beautifully maps out the biological defects and the physics we use to solve them. So myopia, caused by excessive lens curvature or an elongated eyeball, gets corrected with a concave or diverging lens to push that focus back where it belongs. Hypermetropia, where the focal length is too long or the eyeball is too small, needs a convex, converging lens. And lastly, presbyopia. This one happens as we age. Our ciliary muscles just lose their flexibility over time. For older folks who might actually suffer from both myopia and hypermetropia at the same time, we prescribe bifocal lenses. The top part is concave for looking far away, and the bottom part is convex for reading.
Section 3. Prisms and dispersion.
Now, let's zoom out to the physics of light itself. This brilliantly illustrates Isaac Newton's famous discovery. He used a triangular glass prism to prove that plain old white sunlight isn't just white, it's actually a hidden spectrum of completely different colors. Because of the angled glass surfaces, light bends when it enters from the air, and then bends again when it exits back out. We call this splitting of white light into its different component colors dispersion. It gives us that classic sequence we all remember as VIBGYOR: violet, indigo, blue, green, yellow, orange, and red. But why does it fan out into this distinct band? Well, it's because different colors of light actually bend at completely different angles. Red light is sort of lazy, it bends the least. Violet, on the other hand, bends the most. So the rays of each color are literally forced to emerge along entirely different paths.
Section 4. Atmospheric refraction illusions.
Let's start this section with a fun question. Why do stars twinkle but planets don't? I mean, we see it every single clear night, but the mechanics behind it? Pure atmospheric magic.
It all boils down to atmospheric refraction. Earth's atmosphere is incredibly turbulent, filled with shifting layers of different temperatures, pressures, and densities. Because stars are so ridiculously far away, they act like tiny pinpricks or point sources of light to our eyes. As that distant starlight travels down through all our messy atmospheric layers, it constantly refracts or bends. That continuous bending makes the star's apparent position and brightness flicker, which we see as a twinkle. Planets, though, are way closer. They act as extended, much larger sources of light. So all the tiny fluctuations coming from the different points on the planet basically cancel each other out and average to zero. Ergo, no twinkling.
Now let's see how this builds into an illusion that literally bends our perception of time. This is a great callback to the daylight extension visual we broke down in our Chapter 10 explainer. Because our atmosphere bends light toward us, sunlight actually curves over the horizon. What does that mean for us? It means we see the sun a full 2 minutes before it actually physically crests the horizon in the morning. And its light keeps bending toward us for 2 minutes after it has technically already set at night. That's 4 extra minutes of daylight every single day, entirely thanks to atmospheric refraction acting as a daily mirage.
Section 5. The Colourful Sky. Have you ever just paused and wondered, why is the sky blue during the day but turns a fiery red during sunset? If sunlight is white and has all the colors, why does the sky change its look so dramatically?
Well, the answer lies in the Tyndall effect and something we call the scattering of light. As sunlight punches into the atmosphere, it smacks into fine, microscopic particles in the air. During the daytime, shorter wavelengths, like your blues and violets, are scattered intensely in all directions by those particles. So our biological camera just processes a massive blue sky. But at sunrise or sunset, the sun is super low on the horizon. The light has to travel through a much thicker layer of the atmosphere just to reach us. By the time it actually hits your eyes, practically all those shorter blue wavelengths have scattered away into nothing. All that survives the long trip are the longer wavelengths, the reds and oranges. And hey, what about clouds? Well, water droplets in clouds are huge compared to air molecules, so they scatter all wavelengths of sunlight equally, which just looks brilliantly white to us. Basically, the distance the light travels and the size of the particles literally dictate the colors we end up seeing.
And that brings us to the absolute most beautiful combination of everything we've covered today, the rainbow. Just a massive, stunning, natural spectrum painted across the sky after a rain shower. A rainbow happens because millions of tiny water droplets are acting exactly like tiny suspended prisms. First, sunlight hits a droplet. Second, we get dispersion. The droplet splits that white light wide open. Third, those newly separated colors experience total internal reflection, bouncing right off the inside back wall of the water drop. Finally, refraction takes over, bending the light one more time as it exits and shooting that glorious separated spectrum straight into our eyes. It's absolutely breathtaking when you break down the actual mechanics of it, isn't it? I want you to think about this as we wrap up. If our biological cameras can process all these incredible daily illusions, from flattened, time-delayed suns to bent, twinkling starlight to giant water prism rainbows, what else out there in this massive universe are we not seeing exactly as it really is? Keep questioning, keep observing, and thank you so much for joining me for today's explainer.